Okay, so we are on Module 7, and we're going to be building on what we learned in Module 6. So we're going to be looking at more difficult balancing of chemical equations today. Some of it gets a little tedious, so I hope you're not sleepy. Yeah, oh, sorry. Yeah, we're all sleepy a little bit, right? Remember, next week we have off. We can sleep next week, okay? All right. So we're going to be looking at the basic kind of chemical reactions, some difficult equations, and we're going to get started on something that is a real meat and potatoes of chemistry called stoichiometry. All right, so we're going to get started on that today. And then, am I right? If this is our last module before our midterm, does that sound right? Is that right? Yeah, I guess so. So what we're going to have is today we'll be doing the lecture. You'll have next week off for Thanksgiving. The week after that, you'll come back for a quiz on Module 7 and a lab on Module 7. Then the next week we have what's called a review week because there's an extra week in the first semester this year. And then the week after that, we will do the final exam. And you will have Christmas break after that. Okay? So during that review week, we can, if you have any questions, specific questions or something like that, I'm going to give you an idea of what to study for the midterm. All right? Okay. Okay, so we're going to learn today about how we can count molecules and count atoms in chemical equations. And when we do that, we can predict what the chemical reactions are going to be. All right, we're going to be learning something important today, the concept called the mole. Who has heard of the mole? When it refers to chemistry. Yeah? Okay. Are you afraid of the mole? I was always very frightened of the mole. Yeah. So, but I'm gonna dispel all the fears of the mole today. All right. That's going to be the second half of our lecture. All right. There are 4 basic chemical reactions we'll be learning about in Chemistry 1, and this is your first set of blanks at the top of your book right there. Number 1 is called formation, and we're going to go through each one of these one at a time. There's going to be a few things you're going to need to know about these because what's going to happen is you're going to end up writing out chemical reactions, a chemical equation, without me giving you all the information. All right, so you're going to have to figure it out because we're going to look at the kind of reaction it is. So if it's a formation reaction, we're going to take 2 things and make 1. Okay, or we're going to have a decomposition reaction. We're going to take 1 thing and make it 2 or 3. We're going to decompose it. We're going to break it down to its separate components. We're going to have combustion, which we already know a little bit about combustion. That's burning. Some of the most difficult of the balancing equation groups are found in the combustion group. We're going to actually go through that extra credit one from the quiz. A lot of y'all got it. I was very proud of y'all. A lot of y'all got it. And we're going to learn today when it comes to those balancing that fractions are your friend, regardless of what you've thought your whole entire life. Fractions are indeed your friend here. And then acid-base reactions. I don't believe your module lists that. It just lists the first 3, and that's because acid-base, we have a whole, module or 2 coming up on just acid-base reactions. We just want to make sure you understood that that's one of the 4 of the basic chemical reactions we'll be learning about this year in chemistry. All right, let's start with decomposition. So we're going to take something. It's a reaction that changes a compound into its constituent elements. We're going to take CO2 in its gaseous form, and we're going to break it down into carbon, a solid form, and O2. Now, if I just gave you CO2 and told you this is a decomposition reaction, I would expect you to know that that means C plus O2. All right, I'm just going to write the balanced chemical equation for the decomposition of CO2. And that's all I give you. And you'd say CO2 yields C plus O2. Now, is this a balanced equation? It is, isn't it? Yeah? It's balanced. Good. Yay. All right, here's another one. We're going to write the chemical equation that describes the decomposition of ethanol. Ethanol is C2H6O. That's all the information you've been given. So where would we start with that one? We're going to decompose C2H6O. So we would say C2H6O yields me what? Carbon plus hydrogen plus oxygen. Right? Easy breezy. There we go. That's all you need to know for that. Except there's a couple of things you have to remember. What do you have to remember about oxygen and hydrogen?
Pairs.
What are they called? Homonuclear diatomics. So on the right side of the equation, you're going to have C plus H2 plus O2. Do you get it? All right. Remember I told you can never mess with those little subscripts? Well, in this case, you have to, because there's no such thing as just O by itself. It's always O2, right? So you have to know that. All right, so we're going to watch our esteemed author of the book go through this. And I'm telling you, it drives me crazy too. It really does, okay? But he's going to go through every step, painstakingly through every step, okay? Including bringing in, as far as I remember on this one, some of those fractions, okay? And so listen, don't fall asleep. I should have brought a pot of coffee for y'all this morning, okay? Don't fall asleep. And because we have a couple of these today where we're going to have to, because his voice is really quite hypnotizing, where it makes you just sort of, you know, especially if you're already sleepy, like me. All right, so here we go.
Example, we're trying to come up with a chemical reaction that represents the decomposition of ethanol. Now the chemical formula for ethanol is given to you, C2H6O. All right, well let's start with that chemical formula. The thing decomposing is C2H6O. It's the only reactant because in decomposition reactions, the only reactant is the thing decomposing. So then we draw our arrow and we come up with the products. What are the products in this equation? Well, the products of this equation are simply the elements that are in the molecule. What are the elements in this molecule? Well, the first one there is carbon. Now, we usually represent an element by simply giving its symbol. So we just put a C on the product side of the equation, and that tells us that carbon is a product. The next element is hydrogen. However, I can't just write H on the product side of the equation for hydrogen. Why? H is a homonuclear diatomic. That means hydrogen gas, the elemental form of hydrogen, doesn't exist as a bunch of H atoms. It exists as a bunch of H2 molecules. So I can't write just H on the product side. I have to write H2 because that's the actual chemical formula of the element hydrogen. The next element is oxygen. Same thing here. Oxygen is a homonuclear diatomic. The element oxygen does not exist as oxygen atoms. It exists as O2 molecules. So I have to write O2 as the last product in this chemical reaction. Okay, there's a chemical equation. C2H6O makes C plus H2 plus O2. The problem is this chemical equation is not balanced, so it's not a real chemical equation. Look at the carbons. There are 2 on the reactant side, only 1 on the product side. So I need to balance the carbons. First, let me rewrite the equation. Then, we'll just stick a 2 to the left of carbon. That gives me 2 carbons on the product side as well as 2 carbons on the reactant side. Now realize I couldn't have put a 2 there as a subscript because there's no such thing as C2. However, by putting 2 as a coefficient to the left of C, that just means 2 carbon atoms. Carbon atoms exist, and I can have 2, 3, 4, or 5 of them. So C2 doesn't exist. I can't just make C2 out of thin air. So I can't add, remove, or edit subscripts. But I can put numbers to the left of the elements or compounds in a chemical equation, and that's what I've done here. Put a 2 to the left of C to balance the carbon atoms. All right, now let's look at the hydrogen atoms. There are 6 hydrogen atoms on the reactant side and only 2 on the product side. So we need to balance the hydrogen atoms as well.
That's easy.
So let's rewrite the equation.
That's easy.
And now let's see what we can do. We don't want to mess with C2H6O because we've already balanced the carbons. If we put a number in front of C2H6O, we'd have a problem. Our carbons would be out of balance. So instead, let's see if we can put a number in front of H2 in order to balance the equation. And we can. If we put a 3 in front of H2, then I'll have 6 hydrogens on the reactant side and 6 hydrogens on the product side.
Everybody sees that, yes?
So now the hydrogens are balanced as well. Well, there's only 1 element left to balance, so let's balance it. There's 1 oxygen on the reactant side of the equation, 2 oxygen atoms on the product side of the equation. How do we...
Okay, I'm going to stop it right here for a second because I'm going to say, who sees it right now? Who's got it? Okay, do you got it? You know what's happening? Okay, some of you? Okay, because right here, he's going to go through this step now of the fraction. So if you can see, because I can even see it, and I'm not good at chemistry. And I'm like, why do we have to go through all these steps? Well, because if you go through all these steps, you'll get it. Okay? If you go through every step, you'll get it with the silly, ridiculous fraction that we're fixing to put in there. Although I will tell you on this one, the fraction is pretty easy because I've got a 2 I'm dealing with. I've just got a 2 right there. And so my fraction will be 1 over 2. I can cancel out my 2's, basically, kind of as a little math thing right there. Okay. But You don't have to go through the fraction step if you can get it. Okay? There's just one step if you do not do the fraction part you might forget to do. All right?
Balance that. Should we put a 2 in front of C2H60? Well, that would certainly balance the oxygens, but then the carbons and the hydrogens are out of balance.
But could we do
If
that?
I put that 2 there, I get 4 carbons on the reactant side, and there are only 2 on the product side. I get 12 hydrogens on the reactant side, and there are only 6 on the product side. So even though that makes it easy to balance the hydrogen, it ruins the other balancing we did, so we can't put a 2 there. What are we going to do then? Is there any way to balance this equation? Well, yes there is. Let's put a 1/2 in front of the oxygen. Now look what happens. Got 1 oxygen on the reactant side. Then how many oxygen atoms do I have on the product side? Well, we take the number of oxygen atoms in the molecule, 2, and we multiply by the number of molecules, in this case 1/2. 2 times 1/2 is 1. So now the oxygens are balanced. So now we have a balanced chemical equation.
Never leave
2
a
carbons
fraction
on
in there,
each
y'all.
side,
Never do it.
6 hydrogens on each side, 1 oxygen on each side. That's great, but it's not really physically reasonable, is it? Remember what those numbers to the left of the substances in the chemical reaction are supposed to represent. They're supposed to represent the number of participants. 2C means 2 carbon atoms. 3 H2s means 3 hydrogen molecules. 1/2 O2 doesn't make any sense. You can have 0 oxygen molecules, or you can have 1 oxygen molecule, but you can't have 1/2 of an oxygen molecule. So even though our equation is balanced, it's not physically reasonable, and we need to make it physically reasonable. How do we do that? Well, we need to get rid of the 1/2. But we need to do so in such a way that it does not destroy the balance of the equation. How can that be accomplished? Well, you just have to remember one little fact about chemical equations. They behave just like algebraic equations. You can do any mathematical manipulation to one side of the equation as long as you do that exact same manipulation to the other side of the equation. Well, think about that 1/2 there. If I multiplied the product side of the reaction by 2, that 1/2 would disappear because 1/2 times 2 is 1. However, if I do something to one side of the equation, I have to do it to the other side of the equation. So I also have to multiply the reactant side by 2. Now all we do is plug through the math. When I multiply the reactant side of the equation by 2, C2H60 becomes 2 C2H60. I had 1 C2H60 molecule before, now I have 2. On the product side, if I multiply the product side by 2, I have to multiply every term by 2. So 2 carbon becomes 4 carbons. 3 H2s becomes 6 H2s. And then 1/2 O2 becomes 1 O2. Now we can see this chemical equation is still balanced. There are 4 carbons on the reactant side, 2 in the molecule, but I got 2 molecules, so 2 times 2 is 4. 4 carbons on the product side. There are 12 hydrogens on the reactant side and 12 hydrogens on the product side. There are 2 oxygen atoms on the reactant side and 2 on the product side. So that's our balanced chemical equation, and that's the proper answer.
So if,
Now this little
if we
trick
had,
of using fraction,
if we had put that 2 in front of here to balance that oxygen back here, would you have noticed that you had to change those as well?
Yeah.
Y'all would have got that, right? So I'm totally cool with you doing it that way. All right, so, but if you don't get how you have to do that, because that would be the mistake. You'd put the 2 here, you'd say, okay, good, I'm done, and you'd forget to multiply those 2 by 2. All right, and you'd end up having that incorrect. If you go back like he does at the end and do your accounting to see, okay, is everything, and I would do that if I were you. Once you say you balance your equation, I would go back and account and say, how many do I have on this side? And then you say, whoa, 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 that's not in balance now. Okay, so remember that coefficient right there goes for everything in the molecule, okay? All right. All right, now y'all are going to try it. Here we go. You're going to write out the balanced chemical equation for the decomposition of SiH3F. Si silicon something or other, right? Maybe they gave us the name of it. All right, so that's all I'm giving you. So where do you start? Write down SiH3F, and then draw an arrow. And you're going to have Si plus what? H2 plus? Thank you. Remember, fluorine is also a homonuclear diatomic. So F2. All right, so it won't be balanced. So is it going to be easy to balance? I think it's going to be pretty easy to balance, yeah? All right. We've got 3's and 2's. We can deal with 3's and 2's. What is your first thing you're going to do? Well, first of all, do we need to do anything with silicon? No, it's balanced. So we'll go over and let's try hydrogen. So what are you going to do with hydrogen? So this is where we can, okay, let's go ahead and go through. Okay, let's do it without a fraction real quick and see if you got it. Okay, so what would you do to hydrogen? Put it in front of the entire first equation. Okay, don't start there. Start with hydrogen over here. Okay? Okay, so we can follow where you're going. Would we put a 3 right here? Okay, and then, well, we could put a 3 right there, but if we put a 3 right there, what would we have to do next? Have to put a 2 right there? Okay, and then to fix this, what would we do there?
If you already put a 2 on the other side of the equation.
Yeah, so if there's already a 2 there, would this be balanced then that way?
Yeah.
Okay, does everybody see what happened? Now can you go, Kat, did you get it? Okay, all right. Well, so we're going to go through it step by step right now, and we're going to bring the fraction in. And it's not as pretty a fraction as 1/2, sadly. All right, because we're doing with 3's and 2's. If you only have 2's, yay, you know, but 3's and 2's, and when you have 11's and things like that, then you're, you know, it's crazy. So, all right, so here's what we can do. We'll start with the hydrogen over there. Silicon we don't have to worry about because it's balanced. So we're going to put in 3 over 2. I'm going to use that fraction. Before I did the 1 over the 2. See, there's my little trick right there, my 1 over my 2, my 1 on this side, my 2 on this side, right? So my 3 over my 2 there. All right, so then I can kind of basically ignore those 2's right now. Just for now, I can ignore those 2's. So I can say that that's balanced for the hydrogen, okay? And then I've got my F2 here. So what do I have to do to get that 3? Is that my next step? I'm going to get that 3/2 out of there. No, actually, I'm going to go ahead and put my fraction in here, which is easy to understand, putting my 1/2 there. Do you see how I got that? My 1 over my 2. Get it? Okay. So I've got that. Now I'm in pretty good shape. Now what do I want to do?
Multiply by 2.
Everything to get those fractions out. Can I get both of those fractions out of there if I multiply everything by 2?
Yeah.
Yes. Hallelujah, right? So I'm going to multiply everything by 2 on both sides, and I get 2SiH3F, 2Si. That's where the missing thing would end up happening if you were not careful. And, oh, okay. I'm going to multiply those by 2, 3H2 and F2. Okay. All right, so if you got it the first way by seeing it, that's great. All right? But if not, go ahead and do those fractions. And my little trick with putting the 3 over the 2, the 1 over the 2, that's my little trick. Okay, my little cheat. I hope it works every time. All right, so that I think you were supposed to write that one down there in your book, yes. And furthermore, these 2 ones we just did, that previous one, the combustion one, and now not a combustion one, that carbon one, and now this one, those are like 3 or 4 pages in your book, literally 3 or 4 pages. So if you've got it down here, you can like skip those 3 or 4 pages as you're reading, okay? Or just skim through it to remind you what happened. In other words, that painstaking video that every word of that is in your book. Just about, okay? All right, next we have formation. Now the formation reaction is one that starts with 2 things and ends up with something big, right? Produces 1 compound. So I'm going to look here at chlorine, so I've got Cl2 plus C2H2, both gases, and I'm going to end up interesting with a liquid called C2H2Cl4. Now, the question is it balanced? Right off the bat, you can tell me no, right? Because I've only got 2 Cl's here, and I've got 4 there. I just need one thing to throw it out. The carbons and the hydrogens are all right, so really that's the only thing I have to deal with. All right, so can we balance it easily? That's pretty easy, isn't it? Now it's balanced, isn't it? All I had to do was bring a 2 up there. Do you see that? Am I balanced now? Yeah. All I had to do was put a 2 in front of my Cl2, which gives me 4 Cl, and there we go. And now we're going to try one that's a little more difficult. So this is the one I think you're supposed to write down. This is, write the chemical equation for the formation of MgCO3. So we have 3 things in there. We have magnesium, we have carbon, we have oxygen. All right, so we're going to write a formation equation. So if we're going to be forming this. So that's going to be my product on the right side, my product side. All righty, y'all ready? So to get that product, I'm going to have magnesium, carbon, oxygen, but it has to be an O2. All right, is magnesium one of my homonuclear diatomics?
No.
No, no. So we don't have to, and carbon we know is not. So are we almost balanced? Just that 2 and that 3 right there. Okay, am I going to do fractions on this one? Let's see. All we need to worry about is the oxygen. There it is. We are bringing in our 3 over 2 right there. And then multiply the whole thing by 2. And I end up with my 2's everywhere except for my 3 right there. Now, remember that step right there? Could have skipped it. Did y'all see it before I put that step in?
Yeah.
Okay. It's just by putting that step in there, you won't forget to multiply everything by 2. That's all. All right, so formation. for the decomposition and formation reactions, you have to remember your homonuclear diatomics. So we have hydrogen, we have nitrogen, we have that whole row of 7, right? What was our little mnemonic? Can y'all remember what it was? Something about cold beer.
It's in my
Something fear, something.
Have no fear of ice cold beer.
Have no fear of ice cold beer. Yeah. Okay. All right. Combustion. These are the ones, if you ask me, are the most difficult. But honestly, when we look at these, and some of those of you, a good few of you who got that extra credit on there, the fractions will be super helpful on this. Super helpful. All right. Combustion reactions require oxygen. You need to remember that forever and ever and ever. You probably already know that. You already know for something to burn, oxygen must be present. That is the chemical equation that's going on there. That's the chemical reaction. The longest time scientists thought some weird thing called phlogiston was being used up, and they finally realized it's actually a chemical reaction taking place. When a substance burns, carbon dioxide and water vapor are formed. Okay, if I give you the words a combustion reaction takes place, you will assume that this is going to be your products, carbon dioxide and H2O, CO2 and H2O. If there's something burning besides a carbon-based substance, then you can't end up with CO2 and H2O. That's a special time. We'll look at that in a minute. It's called the combustion of metals. If there's enough oxygen, carbon monoxide, if there's not enough oxygen, carbon monoxide will be formed due to incomplete combustion, which can be deadly. So the 3 kinds of combustions we'll study will be combustion of metals. That is the exception to this rule right up here, the carbon dioxide and the water vapor. Complete combustion, which is classic, and incomplete combustion, deadly. All right, complete combustion. A reaction in which O2 is added to a compound containing carbon hydrogen producing CO2 and H2O every time. Every time. For instance, I start with C7H16. I already hate this one. I already hate it. H16 plus O2. So if I gave you, we're going to combust C7H16. That's all I told you. Then you would say, okay, I'm going to add O2 to it, and I'm going to end up with CO2 and H2O. I'm going to assume you're going to know that's what the equation's going to say. The only thing I'm going to give you is C7H16. Also, remember we have our liquid, gas, gas, gas in those little parentheses right there. They're not that important right this minute, but another module coming next semester, they will be important. So that's why they keep throwing them in at this point in time. They seem a little clunky and awkward to me, but that's what those are standing for right there. Okay, so first question is obvious. Is it balanced?
No.
Sadly, no. We have some crazy, crazy numbers like 16 and 7, an odd number. So what's the first thing we can do? Well, okay, here's my first deal. I'll tell you. The last thing you want to balance here is going to be our oxygens, and that's because they're found in 2 different places. So let's start with the things that are found in just once on each side. We have a H only once on this side and an H only once on this side. We have a carbon only once on this side and a carbon only once on this side. So let's start with our carbon. I think there's only one thing we can do with our carbon right now, right? What do we do with our carbon? We have to put a 7 as our coefficient, right? I think we have to do that. Yeah, right there, we have to do that. All right, so, I added another step in here. Bummer. Okay. Look what I did with my oxygens right now. Okay, so my 7 is going to do what to my oxygens?
Make it 14.
Yeah, I think we should go with, can we go to hydrogen real quick? Let's go to hydrogen. So my hydrogen right here, I had 16. I had 2 on this side. Putting an 8 in front of it fixes that. Okay, it fixes that. So now we have to go account for our oxygens. So what did that do to my oxygens? I have 7 times 2 here, 14 plus 8. I hope it's 22, right? Okay, so then, actually, I'm in pretty good shape. So now all I have to do is go back here. I've got a 2, and can I easily make my 2 into 22?
Yeah.
Don't you love 11? 10's and 11 multiplication, besides 0 and 1. Those are the best, right? Okay, those are the best. So right now, am I balanced now? I think I am. Yes, that's balanced. So that one really wasn't so bad, even though we end up with some messy numbers like 11 and 7 and this kind of thing. It's not too bad. So, but I wish I'd put an extra step in there, even the fraction. Maybe in your book it puts the fraction in there. But I did skip fractions. Are we okay? Everybody good? Okay. All right. Write the balanced chemical equation for the combustion of butane. Oh, this is our extra credit on the extra credit from the quiz last week. Okay? So, I'm going to give you C4H10 and you're going to tell me what's going to happen to it. What's my equation? Just tell me what the equation is. Just go ahead and write it down. C4H10 plus what?
O2.
O2 yields me what?
CO2 plus H2O.
Okay. And that's it? Right? That's your equation. Very good. Everybody got that? If I tell you combustion, always in your mind say CO2 and H2O, CO2 and H2O, CO2 and H2O. And don't forget to add your O2 on the front. All right. Must we? Y'all want to do it without it?
Yes.
Really?
Yeah.
Are you going to help me? Okay. All right. Let me get a marker. So tell me my original. C what?
C4 H10 plus O2.
Oh, that was it? C4H10?
Yeah.
Okay, here comes my O2. And it's going to give me what?
CO2 plus H2.
Okay, where are we going to start? Let's start with carbon. What's our first thing we're going to do?
We need to put a 4
Right
as
here?
a coefficient. Yeah.
Right there. Now, before we mess with oxygen, let's go to hydrogen real quick. Can we fix it?
Put a 5.
Yeah, right here, a 5. Right there. Okay, good. So we're really, really good, y'all. Except for oxygen. Really the thing that messes up on oxygen is the fact that there's that single one right there. Right? Okay, so how many oxygens do I have on this side?
5.
I've got 4 times 2
8
plus 5
is 13.
is 13. All right, so 13. So what's my next thing I have to do then? Because sadly my 11's not going to work here. I've got 13. So how can I fix it? So how many do I have on this side? I have 2. How many do I have? What did I say having on this side? How many? 13. So what am I going to do with my, let's do our fraction. What can I do? I'm going to move this plus over here a little bit. My 13 over 2. Now, do you see how I got my 13 over 2? Does everyone see how I got my 13 over 2? You see where I got it? I had 13 on this side. I had 2 on this side. 13 over 2. I did that right? Okay. All right. Now, to get everything fixed, to get my fraction out of there, what am I going to do? Everything by 2, which will bring me what? 2 C4H10 plus, that's a 10. 13 O2. Do you see what happened there? Cancel, cancel. And then I had yields 8 CO2 plus,
H2O.
how many did you say? 10, right? 10 H2O. And we're finished. So not too bad. But on this one, y'all, for me, on this one, the fraction helped me. It helped me because it wasn't over 1 for 1. It was over the 2. Because otherwise I'm looking at that 13. Now I didn't necessarily see the correlation between the 13 and the 2 until I put that fraction up there. Do you get it? How do y'all feel about that one? Okay. All right. Now I gotta erase. I think I went through it more quickly than you did, yeah? All right. Those watching on the on the recording. So sorry you didn't get to see this. All right, they missed this. I'll send you a note on that, students watching on that recording. Okay, so that was our complete combustion. Let's look at our combustion of metals. All right, in this case, we don't have any carbon. We don't have a carbon fuel we're dealing with right here. All right, so like for instance, we're going to be doing magnesium. When we get together in 2 weeks for our lab on this deal, we will burn some magnesium. And we will go outside to do that because that is how I set off the alarms at the last time I set off the fire alarms, was burning magnesium. I do it in my house all the time, no problem. But things are sensitive apparently, but we'll do that outside. So I have magnesium and I have oxygen. And what am I going to make? I'm going to make MgO, okay, and it's going to turn into a solid. We'll see that. So, that's a combustion of metal. So in this case, I'm not making CO2 plus H2O. But in other cases, all other cases, if I'm asking you about combustion, I'm going to assume that you know whatever I have plus O2 gives me CO2 plus H2O. You get it? Unless I'm asking about metal, which I don't think I will. So what about this? We have iron and oxygen making this, which is called rust. So is that a combustion reaction? Yeah, technically it is. It's a very slow and not as dramatic of a reaction, but it is. We call it oxidation at that particular point in time. And it causes rust. Okay, so we're going to watch a little video on the combustion of magnesium. Here we go. Is it going? Yeah. Oh, I forgot.
Burning methane. I'm going to take a strip of magnesium and stick it in that flame to get it hot, all right? Now it's getting hot. Pretty soon it's going to catch fire. There it goes. Now the magnesium itself is burning. Notice the white flame, and also notice the stuff coming off. That little spiral of white stuff is magnesium oxide, the
Solid.
product of this chemical reaction. So magnesium reacts with oxygen to make magnesium oxide. That's combustion, and this combustion results in a nice white, bright flame.
By the way, that's what fireworks are. It's just combustion of magnesium with some salts added in to make different colors. Pretty cool. All right, so complete combustion. I start with the fuel. Now we're talking, about now the H2O and CO2. Okay, I start with my fuel, which is carbon-based. I add my oxygen to it. I give it we'll learn later about the activation point. There has to be combustion needs a high activation energy, it's called, and that's very good. Otherwise, things like the logs sitting outside would just burst into flame because there's oxygen all around the dead wood outside, right? And they would just burst into flame. But there has to be an activation energy, which for our fireplace, we would add a match or, burn some paper or something like that. All right, and we're going to end up with CO2 and H2O. That's beautiful. That's my complete combustion right there. Incomplete combustion, however, is when I start burning, look, same fuel, same oxygen, but I go through the reaction, and what happens is the fire starts burning really great. I mean, it starts really getting hot and flaming and going, and there's not enough oxygen getting into it. So therefore, it's like it's starving for oxygen, so it goes through this incomplete combustion where instead of making CO2, I'm going to share those oxygens now, and make CO, carbon monoxide, which is deadly to us. And then even later, it's still burning. I'm still running out of oxygen at this point. Then I'll end up with just making carbon itself. Who has a fireplace at home that burns real wood? Yeah, you'll have real wood fireplace. Have you noticed that the black soot is all around it? You know what that is? That's carbon. It's carbon that's there because you had a nice hot fire. What else was that thing making? It was also making carbon monoxide. Okay, where was that carbon monoxide going? Hopefully. Up the chimney, right? Up the chimney. That's where you want it to go. All right, because if you're burning something and having a combustion reaction and you're producing heat, so like say a heater or something, then you are going to end up producing some carbon monoxide in that just because of the fact that the heating is going to be robust, right? A big fire, this kind of thing. So for instance, if you're in a small place, let's say a camper, and you have a kind of heater that uses a flame. I'm not talking about an electric heater, y'all. That's different. That's using resistance of electricity. That would be safer if you were in a camper. If you're using a gas-powered little tiny, deal, and you're in a small place like a camper, open a window. Don't do it, because it's possible you could make enough carbon monoxide that you could poison everybody in that camper. My parents, we used to go camping when I was a kid, and my parents said there were There was one time when we were at a place, it was cold, and one morning the neighbor campers, they didn't come out. And that's because their heater had created enough carbon monoxide. They were all dead in there. I didn't know it at all. My parents told me that when I was much older. I would have been traumatized by that. So carbon monoxide is going to be formed if we're using a flame. In your house is big. No worries. But most of you probably also have something called a carbon monoxide detector. Yeah, we have one. Batteries out. So don't worry. But you should have a carbon monoxide detector. I will also tell you that carbon's heavy. Carbon dioxide and carbon monoxide are heavy. They drop to the ground, and so therefore it's where we are. So it's down here where we are. So you know how when a fire you're supposed to crawl out? Well, that's when the carbon monoxide is going to be right down there on the ground because it's heavy. All right, so incomplete combustion reaction, there's not enough oxygen. You can see right here, incomplete. On the bottom here we have our CO being formed along with our CO2. That's all that's saying. Same thing, make sure you have enough ventilation. And so it turns out that we have a catalytic converter in our cars which actually takes that incomplete combustion and adds it back in. It uses a metal to add it back in. You need something back on here?
Yes.
Y'all need to write something right there on a blank. Okay, so complete combustion and then incomplete combustion. All right, and next in your book it says decomposition of sugar. We'll do that next time we get together. So, you know, when your car is burning, it's burning fuel in it. Most of us, I don't know if somebody has a fully electric car out there. Anybody driving a Tesla out there? No? Okay, so even if you have a partially electric, you still use some gas in that, a hybrid or whatever. When you burn there, you're going to be making carbon dioxide because you're burning, and then some of it's going to end up carbon monoxide. You already know this, right? That if you're in a garage and you start your car, you need to open that garage door because you're going to be putting carbon monoxide in there. And so one of the things we've done with our, are we all good on our blank here? Yeah. Is we put a carbon, we change it in our cars now in that catalytic converter. There's actually metals that act like a catalyst that will put that oxygen back on that CO and make it CO2, or take it apart, one of those. I think we'll get to that when we talk about catalysts and see how that works right there. It has to do with right here, all right? All right. Now, that was the fun part of our module. Yeah, here comes the hard part, okay? Yikes. All right, so we're going to be needing your periodic chart of the elements at this point, okay? Because we're going to be looking now. We already know what the chart tells us about the number on the top, which tells us how many protons are in our atoms, right? And we know our symbol, of course. And then at the bottom, we're going to be looking, we're going to key in on this bottom number right now. In fact, from now on for the rest of the year, pretty much, that little bottom number, that little mass number down there is going to be your best friend. Okay, we don't even care about protons so much anymore. We don't care about electron configuration so much anymore. What we care about now is the AMUs. So AMU stands for the atomic mass unit. All right, if we're looking at one atom of helium, it's going to weigh 4.003. 4.003 what? That's the question. We had to come up with this thing, this unit called atomic mass unit, because we already know something about helium. It's very lightweight, yes? It floats in a balloon, right? Well, if we have one atom of it, can you imagine? That is very, very light. It's so light there's not a single thing on the planet that could weigh it. We don't have a scale that is sensitive enough to weigh that. So we've come up with some, how did we get that number? You may wonder. We got that number because these smart people all figured it out by doing a bunch of math. All right, we ended up with this number. They divided it down on something we could weigh, okay? In fact, we weigh things in grams. That's the only way we can weigh things, really, in grams. All right, so we're going to take that number now, our atomic mass unit, and this is going to help us to understand how we can actually make chemistry practical. Believe me, chemistry is practical. I might even argue chemistry might be the most practical science out there. Everybody needs a chemist, okay? And you've got to be able to figure out how to make chemicals. And in order to make chemicals, you've got to put things together, and you've got to put the right amounts together, and this is what this is going to tell us right here. All right, so First of all, when we calculate those molar mass units, remember I told you about that math that somebody did a long time ago? Okay, they figured something out. And they figured out that AMU, this atomic mass unit, is equal to 1.66 times 10 to the negative 24 grams. I have a star by that. What does that mean? 1.66 times 10 to the negative 24. That is a small number, isn't it? Doesn't that make sense? This is 166 with 24 zeros in front of it. That's how small this is. It's a negative 24. I have 0.24 zeros, 166. All right? So we're going to use that number to find out how much we had for our AMUs. Okay, we can count the number of molecules in a sample, this kind of thing. But we can't use such a tiny number. Although your calculators do have that little feature, yes, where you can put that to the negative something. Yes, everyone? Okay, because that's going to make your quiz much easier if you have all that on there and not have to keep track of those zeros. All right. Okay, so we're going to come up, you find it at the bottom of the box of each element on the periodic table. The AMU is down there. Okay, so remember, what was it, 4? It was 4 AMUs for helium. All right, so we multiply that by 4 to get the number of grams that was, which would actually bring our 24 down maybe at that point. All right. Do y'all need that? Mm-hmm. So where do you find that number for an element? At the bottom of the box. It's your mass. It's your mass. We're not even in part B yet, are we? We're still in part A. Yeah. So there's 2 of these weird, crazy numbers you're going to have to remember. And this is one of them. 1.66 times 10 to the negative 24. Okay, you're going to need to remember that number to do some math with it on your quiz. All right, are we good? All right. What is the mass of a nitrogen atom? Oh no, it's asking for it in grams. Well, here's our relationship. So that is a conversion relationship. 1 AMU equals this many grams. So that's all we have to do. All right. So what is the mass of nitrogen in grams? We know there's our conversion relationship. Look at the chart to find the mass of nitrogen. Look at the bottom of the box. Is it 14? All right. So this is the number we know. And remember what I've taught you from the beginning. You always take the number you know and put it over 1. Start there. Start there. So I took the number I know, 14.0 AMU over 1. And now I'm going to do my conversion. I've got my AMUs and my grams here. So now I can do this 1.66 times 10 to the negative 24 grams over 1 AMU. Everybody sees that conversion. Everybody got it? Then I do the math. And trust me, your little calculator, don't forget it. Because you don't want to be counting these zeros in your head. You're going to be writing those down. And you're going to come up and you're going to end up with 2.32 times 10 to the negative 23 grams. All right, so what if I asked you, would you please weigh out 1 AMU of nitrogen? You would have to weigh out 2.32 times 10 to the negative 23 grams. Do you think my scale, my really excellent, awesome scale, is going to do that?
No.
No. All right, so what's going to happen here, y'all? What's going to make this practical is the fact that I can actually work with grams, which is something I can see. If I ask for 5 grams of nitrogen, we can do that. Let's say something more. Let's say sodium chloride, something we can actually see. Because this is going to end up, I think, nitrogen being a gas. All right, so we're talking about the mass of each thing. So if we look at a molecule now, we can do the same thing for a molecule. All right, so I have CH4. I have 1 carbon, that's 12. And I have 4 hydrogens, which is 4 times 1. So that 12 came from the chart, that 1 came from the chart. So here I can see my molecular mass for CH4 is 16.05. Don't worry about that right now, that unit, 16.05 AMU. Get it? 16.05 AMU, atomic mass units. So you add them all together. Just do some addition. And the addition has to come, you have to have your chart for that. You must have your chart, because you won't be able to remember those numbers. All right, so if you add all the masses of all the atoms in a molecule, you'll get the mass of the molecule, which equals the molecular mass. Okay, that's your blank right there at the bottom of page 49. And now we're going to do an example. Okay. What is the molecular mass of CHCl3? Okay, so get your charts out. I don't even have my charts today. I don't know why I have charts. Everything out of there. Okay, I know C is, what is C? 6? H is 1? What's CL?
The bottom number?
Yep, the AMU at mass number. C is 6, right? Oh, 12. Sorry, 12. H is 1, so I have 12 plus 1, that's 13. What's CL?
35.
And how many do I have of those?
30.
What's 3 times 35?
105.
Oh, nice. And now add all three of those together. Let's put them out. Okay, here we go. 1 times 12 plus 1 times 1 plus 3 times 35. Does everyone see where I got those numbers? Everybody sees it? 119.5 AMU. That's your answer. That's not bad, right? That's fine. You just have to remember that we have those 3 of those. So really you could have said 12 plus 1 plus 35.5 plus 35.5 plus 35.5. And you get 119.5. Now the next question is asking for the mass of Si6F12O6, but it's asking for it in grams. So what we're going to have to do with that was we're going to have to go this route first using our chart, and then we're going to have to convert with that number, that negative 24 number. Get it? Okay, are y'all ready for this one? Mm-hmm. All right, so somebody tell me SI.
28.
28? And how many do I have? 6? Okay, fluorine?
19.
19, and I have 12 of those. Oxygen that's 6. That's 12 times 6. All right, so let's do that. All right, 6 times 28, 12 times 19, and 6 times 16 gives me 492.6 AMU. Does everybody see where I got that? Okay, so the bottom line to the question is, it's on the bottom line of the chart. Get it? Okay, but now I got to convert it to grams. So I'm going to take this number right here, and I use my conversion relationship. I actually have a video. Do y'all want to go through that video? We're going to have to do it ourselves. I did shorten the video. Forgot my notes too. Okay, so we're looking at 492.6. And I'm going to put that number over 1, yes? Is everybody ready to go that route?
Mm-hmm.
Let me find my marker thing. Okay. 492.6. Now we're going to have to remind me, my number memory is terrible. Are we good? Okay, here we go. 492.6 AMU over 1 times what?
1.66 times 10 negative 24.
Over 1 AM, that's G, grams, over 1 AMU, yes?
Mm-hmm.
I'm going to cancel my AMUs out, and now somebody has, I can't do that in my head. I can't even do that on my calculator. I don't have a calculator like y'all.
8.17716 times 10 to the negative 22.
It's just giving me a headache. Okay. Okay. Tell me again,
8.17716
716,
times 10 to the negative 22.
and that's grams, right?
Yeah.
Is that our answer?
Yeah. Should be.
You know what I bet you he did? Did anybody else do that, man?
I got it. Because I maybe did it wrong. 8.185.
No. Now, what he's gonna talk about, of course, is gonna be significant figures.
Oh.
I know.
There should be 3.
So if it's our significant figures, we go to we're multiplying. So we go out to 2? Do we use that? Oh, but that's to the negative 24, so I don't think that counts.
It still counts because it's in scientific notation.
Oh, it does?
So those are all significant figures.
Okay. I can't stand significant figures. So what's it going to be then? 8.18
Mm-hmm.
times 10 to the negative 22 grams?
Yes.
Y'all see where I'm going with that? Okay. Y'all, I'm going to have to watch this video afterwards to make sure we're all right. Okay. That was just converting it over to grams, okay? So just using conversion reactions.
Isn't so bad. Now let's move on to the second.
Oh, look, see, it started playing it. All right. All right, module 7B. So lab 14, you're changing over some pages here. Okay, so now that we know what we know, this is one of the reasons why, y'all, I like to put this all in one lecture, because we'd be stopping right now and then doing something, and the next week we'd get together and I'd say, remember all that stuff I told you last time? We got to remember all of that to understand what happens next. I like that we can keep the context here, okay? It helps my brain. All right. So how can we count the number of atoms in a molecule in a sample of matter? Okay, so now we're talking about something besides that mass. So mass was the AMU, so we have that number 1.6 times 10 to the negative 24. Yeah. And so we have that, okay? That's one we're remembering. Now we're going to have another number, okay? But it's not going to tell us the mass, it's going to tell us the number of molecules or the number of atoms that are found in the sample. And the best way to use this practically is to have something between how many do I have on the right, the count, how much I have, the mass, in grams, something I can see, and something that's going to bridge that gap is something called the mole. All right, and the mole is your friend. I wish I had made friends with the mole in high school, because he just, I don't know, taunted me all through college. All right. In fact, I wish I'd had this textbook of y'all's when I was in high school. It would have helped me a ton. So we're looking now at the mole concept. What is a mole of a substance? Here's what you're writing down. A mole of a substance is the weight in grams of a substance determined by the number of AMU from the periodic table. In other words, I can take that number at the bottom of our chart, something given to me, and I can translate that into something I can see with my eyes and weigh on my scale. But I can't do it directly. I have to go through the mole. So this is a way of counting the number of atoms or molecules in a sample of matter. It's constant for each element. We need this because atoms are so tiny. They're so small. All right, here's our mole. There he is. He is our friend, even though he has no eyes, and it's kind of creepy and wrecks your yard. I don't have moles at my house, but I had friends who had them out this direction. And they used to like eat through the phone lines or whatever's buried underneath the ground. Yes, they were terrible.
We have little mole rats.
Oh, really?
Yeah.
So you're near me, so I must
But
have
my
those too.
cat eats them.
Oh, that's why we have cats. All right, so we're going to watch a little video that's kind of fun because we're going to be looking at how we're going to take the, remember I told you we're looking at the number of the actual atoms? So, all right, so we're going to have a certain amount of substance, and I'm going to be able to tell you how many atoms of that substance are in a sample. Okay, it's a big number. It's a huge number. So it's another big number we have to memorize, and it's called Avogadro's number. So you got to love Avogadro. Here he is.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles.
Big number.
This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so that's our next number, is Avogadro's number, okay? And it's a really big number. It's 6.022141 times 10 to the 23rd power. I don't think we're using that. We're using 6.02 times 10 to the 23rd. So Avogadro's number is 6.02 times 10 to the 23rd, okay? That represents how many atoms are in a sample of an element when that sample has the same mass in grams. This is one of the most beautiful things about chemistry, is I can take that number and relate it to the number on the bottom of your chart, your AMU, and I can come up with grams, and if I have grams, I am good to go. I can work with grams all day long because I can see them, I can measure them, I can weigh them. Okay, so that's what's going to help us here with Avogadro's number. I will tell you that his number isn't going to be quite as important as understanding the relationship between the AMUs and grams and the number, okay? All right, and the mole. Bring the mole in there. Which once again, our number at the bottom of our chart is going to be super helpful at this point. So what are y'all supposed to write down for this one? There's just a number, so all you need is 6.02 times 10 to the 23rd. You know, possibly even like on your midterm, you may have the thing, you know, what is Avogadro's number? That might be one of your questions, and you have A, B, C, and D, so you'll need to know this number. Don't get it mixed up with our previous number to the negative 24, right? We don't want to get it mixed up with that. That's a really small thing. This is a really big thing. All right, there's Avogadro. It's kind of, yeah, strange looking. All right, for a given molecule, 1 mole is a mass in grams whose number is equal to the atomic mass of the molecule. For example, remember when he said in the little thing of water, what did he say, 16, what did he say, 18? 18.02 for water. Guess what he did? Guess where he got that number? He added those AMUs together on the bottom for H2 and O. 16, 17, 18. All right? That's where it came from. So it turns out whatever I have, if I put that number in grams, that's a mole. That's 1 mole. That's awesome. I don't know why it works out that way. It's just God figured that out, and Avogadro figured out what God's design was, I guess. So an atom of neon, for instance, has an atomic mass of 20. Therefore, 1 mole, listen, 1 mole of neon weighs 20 grams. It's magic. All I need is my chart. You don't seem as impressed as I am. I'm impressed with this. This impresses me, okay? If somebody had told me this in high school, I would have said, that's it? The light bulb would have gone on. I said, whoa. Then the mole doesn't bother me at all. The mole is my friend. Because all I have to do is you look at my chart, and then I know. All right? So in general, 1 mole of any substance contains, therefore, okay, so here's another thing. My 20 grams of neon, guess how many guess how many atoms of neon are in that 20 gram sample of neon? Guess how many? 6.02 times 10 to the 23rd. Every time. Why is that true? I don't even know why that's true. But it is, okay? So in general, it says here in general, 1 mole of any substance contains Avogadro's number of molecules or atoms of that same substance. The relationship was found by Amadeo, okay? Oh, and he never got credit for it. Poor guy. I hope he was a believer because God's saying, you got it, Buster, you got it. Okay. All right, visual representation. So right now we're going to be looking at 1 mole of each of these things. Okay, here's 1 mole of mercury oxide. How many molecules of mercury oxide are in that beaker? 6.02 times 10 to the... I get the 23 and 24 mixed up, so 23. Okay. This is a mole of sucrose, which is sugar. A mole of sulfur, a mole of copper 3 or 2 sulfate, pentahydrate, sodium chloride here, and copper right there. Okay, so you can see those all are moles. I'll bring y'all a sample of the different mole sizes of things next time when we get together. Okay, you'll be able to see all those. And so you can see they look different, but they all represent the same number. So there's 6.02 times 10 to the 24 here, 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 and here, and here. Okay? All right, so there's our number. 1 mole equals that, which gives us, guess what? A conversion relationship. Conversion relationship. So now if we have a problem, what's cool about it is the relation to the mole concept. When you have a mole of a substance, it has Avogadro's number of atoms or molecules in that sample. That's what's cool about it, if you can call anything about chemistry cool, except endothermic reactions. Oh, that was a good joke. You'll figure that out when we study endothermic reactions. They get really cool. Okay. All right. I'll have to remind you of that joke. I think you're supposed to write something here down. Just say 1 mole equals 6.02 times 10 to the 23rd of anything. Any element or molecule. So we're still talking about 2 different things here. This is the actual number of the atoms or molecules. But then again, to make it practical, what do we want to know? We want to know the number of grams so we can weigh it. But the moles get us there. Avogadro's gets us to moles, moles gets us to grams. And really, honestly, besides just crediting Avogadro with this number and understanding that cool relationship, we don't really need it anymore. It brought us to where we need to be, and it has to do with the mole. What we need is the mole. Okay, good? So atomic mass units in moles. Here we go. The atomic mass unit in AMU will give you the mass of 1 atom. The atomic mass in grams will give you the mass of 1 mole of that atom. So if you look at any chart, anything on the chart, look at, pick one, carbon. Look at carbon. What's the number on the bottom?
12.
Okay, so I know that 12 grams of that, 12 grams of carbon is going to give me 1 mole. You get it? Okay, that's important. A molecule's mass in AMU will give you the mass of 1 molecule. The molecule's mass in grams will give you the mass of 1 mole of that molecule. Beautiful. So we're talking about either atoms or molecules. And we have to add those together. Remember, we have to add those AMUs together. Okay, so here we go. Look what we can do now. We can convert here using our, is that Avogadro?
Yeah.
Okay. Is that 23, right?
Yeah.
Okay. I get 23 and 24 mixed up. Convert using atomic or molar mass here coming to my grams. So I know what I have from the chart in my AMU. I can convert that to moles. I can convert moles to grams. Voila. All right. How many grams are in a mole of calcium?
40.
How'd you know that?
Volume.
It's that number on the chart. It's given to you. All right. It's 40.078 grams. How many grams are in a mole of calcium? 40.7078. So now I can ask you another question. How many atoms are in there?
1.
No, atoms. How many atoms are in 40.078 grams? How many atoms are in 40.078 grams?
6.0.
Yes, 6.02 times 10 to the 23. See my relationship there? Isn't that beautiful? Isn't it like it was designed that way or something? How cool is that? That's so cool. I love it. I love chemistry. Not really, but anyway. Okay, you get it? Oh wait, I want to do that again. Watch. We're going to say voila. Here we go. Voila. It didn't do it. All right, moles are your friend. There he is, sitting there waiting to help you. He's your lab buddy. Making it practical. Once I know the mass of an atom, I can use a conversion relationship that relates grams to moles. This is a very powerful tool. All right, how many moles of fluorine atoms exist in a 50.0 gram sample of fluorine? Can I measure out 50 grams of fluorine? I can. As long as I have a scale that measures 50 grams, I can do that. Take my fluorine, which is poison by the way, put it in a beaker, weigh it, I've got 50. Now, what is it asking us? How many moles? I want to figure out how many moles I have. Okay, we're going to watch the video now. You have to get it down, okay? If we have a second one, we can maybe skip that. Let's watch it.
In this example, we're going to calculate the number of moles in 50.0 grams of fluorine. Now remember what the mole concept allows you to do. It allows you to count atoms or molecules. This is an incredibly important concept in chemistry. You've got to get this. If you don't get this, you'll be lost in most of the remaining modules. So let's understand what the mole allows you to do. Here I've got 50.0 grams of fluorine. That's something that can easily be measured in the lab. I'm going to use that information in the concept of the mole to actually count the number of atoms of fluorine in that sample. Now that's pretty impressive, and that's what the mole concept allows you to do. Let's get to it then. If we're going to determine the number of moles in any sample, we need to look at the periodic chart. In this case, we're talking about a sample of fluorine. So let's look at fluorine's entry in the periodic chart. Here it is. There's a 19.0 under the F. What does that mean?
Right.
Well, it actually means two things. First, it means one fluorine atom has a mass of 19.0 AMUs. That's the first meaning of that 19.0. But it also means something else. It also means that it takes 19.0 grams of fluorine to make a mole.
Easy breezy.
Okay, the first meaning of this 19.0 is easy to understand. It just tells us the mass of the atom in atomic mass units, and that's a unit for mass. So it's just telling us the mass of the atom. What does the other one mean? It takes 19.0 grams of fluorine to make a mole. This tells you a conversion relationship between grams and moles. It tells you that 1 mole of fluorine is the same as 19.0 grams of fluorine. So this number serves as a conversion relationship between moles and grams. We look at the periodic chart, we look at the mass of the atom, and that number also gives you a conversion relationship between grams and moles. In this case, it's telling you that 1 mole of fluorine is the same as 19.0 grams of fluorine. All right. Well, if that's a conversion relationship, then doing the conversion is pretty simple. We take the number we have,
Put it over
50.0 grams
start
of
there.
fluorine. We put it over 1 to make it a fraction. Then we multiply by 1. But the expression we're going to use for 1 comes from this conversion relationship. All right. Now I want grams of fluorine to cancel. So 19.0 grams of fluorine is going to have to go on the bottom of this fraction. That leaves 1 mole of fluorine on the top. All right, so my conversion is 50.0 grams of fluorine over 1 times 1 mole of fluorine over 19.0 grams of fluorine. When I do this, the grams of fluorine cancel, and that leaves moles of fluorine. So when I do the math, I find out that 50.0 grams of fluorine is the same as 2.63 moles of fluorine. The ability to convert between grams and moles, and also the ability to go the other way, from moles to grams, is an incredibly important skill to master. If you don't master this skill, you'll be lost for most of the rest of the course. So get this skill down now. All right, I want to make one point about significant figures.
Let's just,
I report.
we'll just do that. Remember, I really don't care about significant figures. Okay, there may be a college professor who does, however. So go ahead and read that in your book about that. So it had to do with we're multiplying, blah, 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 that kind of thing. Okay, so how did, from here, you see, so when I started with this, all right, how did we get to there? Well, we had to remember that 1 mole equals 19 grams, okay? And it was all right there on the chart. So as long as you don't forget that step, everything's written on your chart for you. Okay, just don't forget that step right there. All right, so the mole concept also works for molecules. So practice finding how many grams. Okay, this is where you're going to be spending a lot of time for the rest of the year, okay? How many grams are in a mole of sodium chloride? All right, so the first thing you need to do is find out our AMUs for sodium. We only have one of them. 22.9, so 22.9. And how many AMUs for Cl?
35.45.
Okay, so we can add those together, I think. I don't know if we want to do that right now. Oh yeah, we're going to go to the periodic table. Find that. Yeah, we're going to add those together. Here we go. 23.0 plus 35.5. Do you see where those came from? The bottom of your chart. Yes?
Mm-hmm.
Add them together, we're going to get up 58.5 grams per mole of sodium chloride. Is that what it asked for? How many grams are in a mole? Yeah. So is that like a super easy question? Because you may look at that question and go, oh, grams and moles, what am I supposed to? It's easy. Don't be intimidated by this one. There's other stuff to be intimidated by, not this. All right, do you get it? So your periodic chart, you do not want to forget your periodic chart of the elements for the quiz in 2 weeks. Don't forget that. Okay, everybody have this one written down? All right. This you already know from our video. How many grams are in a mole of water? 18.015, but remember significant figures. I think maybe we would go with 18. We could go with 18 as far as I'm concerned. 18.0 would be fine with me. Do you see where we get it? 1 plus 1 plus 16. I would have gone with 16. And I would have just finished with 18. Right? So you see how we did that? Not hard. All right. How many moles of potassium chloride are in a 50-gram sample of the stuff? So I can measure. I give you some potassium chloride. That's light salt, by the way. I give that to you. I say measure out 50 grams of that, and you measure it out. You can see it. And then I'm going to ask you how many moles are in there. So where do we start?
I'll do atomic mass of
Chart, right. Chart. AMU of potassium,
30,
AMU of chlorine,
35.
35. I'm going to add those together, right? Oh, so that's 74.6, I assume, yes? Grams in 1 mole of, so how many moles of, now I'm looking for how many moles of KCl in a 50-gram sample. So now I have to, here's my conversion relationship. So I'm going to take my 50.0 over gram over 1. Yes, that's where I always start. And then I'm going to do my conversion relationship. 1 mole KCl over to 74. Does everyone see where those numbers came from? Okay, all right. And we're going to end up with 0.670 moles of KCl. Nice. That's just a sample problem. kind of thing you're going to end up with maybe on the quiz, okay? You'll have several of those to do. I would highly recommend not just your study guide, but your practice problems on this one as well, okay? It's going to give you lots and lots of practice. Really, practice makes perfect on this. On all the chemistry stuff, it really does. All right, so you might be thinking, well, big deal, so what? Yeah, I can find out what the moles are. Okay, well, it turns out we're going to tie all this together with a beautiful Christmas bow for you, okay? Is everybody finished with this? No? And that beautiful package for Christmas I'm going to hand to you is a package called stoichiometry. Very intimidating word. Yes? Okay. All right. Oh, we're going to do example first. A chemist determines that a sample of pure ammonia, NH3, contains 12.311 moles of NH3. What is the mass of the sample? Now that seems more practical here. So, because I'm going to be finding out, what it's going to weigh. I'm looking for it in grams, right? I'm looking for grams. All right, I hate to tell you this, but we have this. Okay. Just means I don't have to do it.
Except it turns it around. Instead of converting from grams to moles, in this case we're going to convert from moles to grams. We know that there are 12.331 moles of NH3. The question is, how many grams is that? Now, whenever we do any conversion between grams and moles, we always have to start by looking at the periodic chart. Ammonia, NH3, has nitrogen and hydrogen in it. So let's look at those entries in the periodic chart. Why do we need to look at these entries? Well, remember what the ultimate goal is. We need to find a conversion relationship between grams and moles. We do that by figuring out the mass in AMU. The mass in AMU also tells us the number of grams it takes to make a mole. So we've got to figure out the mass of NH3 in AMUs. That's pretty easy. Below the nitrogen, there's a number of 14.0. This tells us the nitrogen has a mass of 14.0 AMUs. Therefore, ammonia is going to have 14.0 AMUs plus the mass due to the hydrogens. Hydrogen has a mass of 1.01 AMUs. There are 3 hydrogens in an ammonia molecule, so I've got to take that 1.01 and multiply by 3. When I work out the math, I get a mass of 17.0 AMUs. Calculator actually says 17.03, but I have to ignore the hundredths place because I'm dealing with addition, and in addition we have to look at precision. 14.0 only goes out to the tenths place, so my answer can only go out to the tenths place. So the mass of ammonia is 17.0 AMUs. Well, the mass in AMU also tells you how many grams it takes to make a mole. So the fact that NH3 has a mass of 17.0 AMUs also tells you it takes 17.0 grams of NH3 to make 1 mole of NH3. So that's our conversion relationship. 1 mole of NH3 is the same as 17.0 grams of NH3. Now we can do the conversion. We take the number we have, 12.331 moles of NH3, and we make it a fraction by putting it over 1. Then we multiply by 1, but the expression we use for 1 comes from the conversion relationship. I need to get rid of moles of NH3, so that has to cancel. So moles of NH3 goes on the bottom. I need grams to survive, so they go on the top. So my conversion is 12.331 moles of NH3 over 1 times 17.0 grams of NH3 over 1 mole of NH3. The moles cancel, and I'm left with 209.627 grams of NH3. Now that's way too precise, so we have to figure out significant figures here. 12.331 has 4.
Okay, so you see how we got there, right? So we're just flipping the thing around. We're just finding that conversion relationship right there, and our conversion relationship comes from the information we get garnered from the periodic chart of the elements. As long as you can remember all those, then it's really not difficult. Okay, so now I'm going to show you the magic. Okay, does everybody have everything written down that we need here? Remember, this is all in the book if you need to go to reference it there. Okay, which brings us to stoichiometry. Okay, it turns out the coolest thing ever, y'all. This is like abracadabra magic I'm doing for you right here. That when you look at a chemical equation of a chemical reaction right there, that the coefficient That's the thing we use to balance the thing out, right? The big numbers in the front. Up here to the left of each substance tell you how many moles of substance are there. You see what I'm saying? Did y'all just go, I didn't hear any gasps at all out there, okay? But this number that you just balanced your equations, you just figured out something, not to just balance, but something super important. You just figured out how many moles there are. If I know how many moles there are, I can find out how many grams there are easily by going through my chart and doing all that business. So, look here. The decomposition of hydrogen peroxide, H2O2, into water and oxygen is described by the following equation. 2H2O2 gives me 2H2O plus O2. Am I balanced?
No. Yes.
Right there. Got a 2 here. So look at that coefficient. Look at that coefficient. Now, so that we're balanced. First thing you have to know, are you balanced? We're balanced, okay? So I'm going to relate this thing right here to each of these things right here. If I have 2 moles of H2O2 and I go through this reaction, I'm going to end up with 2 moles of H2O and how many moles of O2? 1. 1. Because I'm relating it. For every 2 of these, I have 1 of these. That's pretty cool, all right? So if a chemist begins with 2.4 moles of H2O2, how many moles of O2 will be produced? All right, so I take my number, 2.4 moles, put it over 1, and then my conversion relationship, I know it's 2 to 1. 1 mole of O2 for every 2 moles of H2O gives me 1.2 moles of O2. Now we're still in moles right here. Yeah. So it's not that practical this second. What would be practical at this point was me to ask you, how many grams is that? Can we find that pretty easily? Yeah, we can go through and find that pretty easily right there. Okay, but isn't that cool, y'all, that those coefficients are they're talking about how many moles there are? That's super powerful. Very powerful. In fact, some of the stuff I talked to you about earlier now with our Avogadro's number and all that kind of, we don't really care about that anymore. Now that we know this is the magic we needed to get to. That was example 7.8. You got that written? Okay. All right. So we're going to wrap it all up here and be happy. If a chemist has 0.234 moles of C2H6O, how many moles of carbon will the chemist get by decomposing the sample? So I've asked you a couple things here, right here. First of all, you have to know, what does decomposition mean? What am I going to do? I'm going to break it down to its constituent parts. So I'm going to have C2H6O. It's going to yield me C plus H2 plus O2. And then we're going to have to balance it.
Your first introduction into the wonderful world of stoichiometry. You'll learn all about this fascinating topic in the next module, so this is just a way of introducing you to it. Okay, what does this first problem ask? It gives you a decomposition reaction. Hydrogen peroxide, H2O2, is decomposing into water and oxygen. And the question is, if 2.3 moles of H2O2 decompose, how many moles of oxygen will be made?
We already know this answer.
Now please remember, moles are just a way of...
Okay. The only way for me to get out of that is to do this, and so sorry for you in the recording. You're going to miss a little bit of this.
These two example problems. 2.3 moles of H2. Alright, this equation isn't balanced, so we're going to have to balance it. I'm going to assume you know how to do that by now. So here's the balanced chemical equation. We can use that to do our stoichiometry. Expression for 1 comes from the conversion relationship. I need moles of C2H6O to cancel, so they go on the bottom. That leaves moles of C on the top. When I multiply these two fractions, moles of C2H6O cancel, and I'm left with moles of C. When I plug through the math, I get 0.468 moles of C. Remember, the coefficients in the chemical equation are exact, so they have an infinite number of significant figures. The only significant figures then are in 0.234. There are 3 of those, so I have to have 3 significant figures in my answer. So the answer is 0.468 moles of C.
Okay, so you see what I did there? I just zoomed through that, and it shows you we had the balance. We related our 2 to our 4, and there's our conversion. Do you get it? Pretty cool, huh? All right, I would have to redo that deal. Okay, and I believe that is it. So next week when you come, oh, actually you have next week off. Don't come next week. We have Thanksgiving break. But the week after that, we're going to have a quiz over this. I need your study guide and practice problems. All right, and then if you start developing questions or whatever for the next week, we'll do our review week. And then the week after that will be your midterm exam. Okay. We made it.